A pseudo inverter is an electronic device that changes a DC voltage to a pseudo AC voltage. Why pseudo? It's because the wave is not smooth like a true AC sine wave. By pulsing the DC voltage off and on at time-sensitive rate and varying voltage level, an AC sine wave is approximated. There are many approaches to this process that may sound familiar to synthesis, such as frequency modulation, pulse width modulation, and etc. Generally, here is how it works. A true 120 volt sine wave is like a circle stretched out over time moving above and below a reference. Normally, it starts at 0 volts, races to its peak at about positive 165 volts, goes back to 0, then down to negative 165 volts, and then back to 0 in 160 seconds. A very simple inverter might turn the voltage on at 40 volts and then turn it off. This will continue until it turns on at 120 volts and then turn it off at 120 volts. Well, this does not produce a real sine wave, but to some electrical load, it is close enough. We can also use the capacitor to smooth out this step sine wave quite a bit. This may be found in the output of the inverting device and the most certainly found in the power supply of the device being powered unless it is simple applied. Flexible electronics has emerged as a new era for applications such as RFID, smart card, smart sensor, and flexible display. The key advantage of flexible electronics compared with silicon technology is the low-cost process and inexpensive and flexible substrates. The prototype of pseudo CMOS logic gate is shown in figure, where PDN represents the pull-down network. This can be used to build fundamental blocks such as AND, NOR, and flip-flops. Well, the figure shows the transfer characteristic of diode load and pseudo CMOS inverters. The pseudo CMOS inverter is shown in the insert and contains 4 monotype, TFT, M diode, and it can be replaced by either a diode or a higher resistance resistor. When the in signal is high, both M in and M down are on and pull out, and the input of M up to low. Since M up is off, the voltage level of out can be as low as VSS. On the other hand, when the in signal is low, both M in and M down are off and the voltage level of out is independent on VDP. If VDP is greater than VDD positive 2 volt, then out can be as high as VDD. The pseudo CMOS inverter can therefore have full voltage swing as a CMOS type inverter with only monotype TFT. The key advantage of a pseudo CMOS inverter are illustrated in the following section. The noise margin can be defined as the side of the largest square, as shown in figure 3, that can be inscribed between the input-output characteristic and the minor characteristic in which Vin is the function of Vout. The inverter has better immunity to noise and crosstalk, and therefore is better able to use as a route boost building blocks for constructing a larger scale of circuit. Low supply voltage is the key factor to reduce the power consumption and also to ease the power circuit design. Figure 4 shows the simulation of the 15-stage diode load and pseudo CMOS ring oscillator with VDD 3.3 volt. For diode load design shown as a dotted line, the voltage swing headroom is greatly reduced and therefore ceases to oscillate. For pseudo CMOS design, the ring oscillate can still oscillate but has a longer gate delay, which is reflected in the larger pulse width as seen in the waveform. This can provide circuit designer a trade-off between circuit speed and power consumption.